humanity could essentially go to a dark ages in terms of how we explore the shortest distances.
We're learning again how to land people on the moon, right? Because it was mothballed for however many
Exactly.
decades.
So I think this is part of it. We're not saying like everybody needs jobs and we just give jobs to any particle physics.
Yeah.
We're saying there is certain information humanity has accumulated, and we think this is valuable, and we need to sustain these directions of inquiry.
Yeah.
It's not about day-to-day jobs.
Yeah.
It's really about the science and the knowledge that we're developing in this field.
What's up, you scholars of enlightenment? Dr. Sam Gregson, particle physicist here again. I hope you've had a fantastic week and have a brilliant weekend in store. Now, today, we're going to be discussing what the future roadmap of high energy particle physics might look like, including which colliders should be built and why. There is currently a huge amount of discussion and debate in particle physics regarding the future roadmap of high energy physics. Deciding which machines should be built is a delicate balance taking into account workforce concerns, economics, geographical constraints, political will, and many other disparate factors. The decision is also complicated by the fact that there are many international players, not all of them easy bedfellows, who could build larger, more precise, more powerful, and more expensive particle colliders. These include the US, China, CERN, and Japan. Today I will challenge 3 particle physicists, each of whom has very strong views about the future of the field, to outline their vision for the future roadmap of particle physicists, and to detail which colliders they believe should be built, and why. Firstly, I'm joined by Professor Jenny List. Professor List is a particle physicist within the Technologies for Future Particle Physics Experiment Group at DAISY in Germany, and leads the topical group Science with Lepton Beams, which studies the physics programs of future lepton colliders and develops supporting instrumentation. Professor List is also deeply involved with the planning of future collider concepts and is an elected member of the executive team of the International Linear Collider Detector Concept Group. She is also intimately involved with cutting-edge high-energy physics technology development and was part of the LEAP project, aiming to demonstrate the creation of polarized electron beams using laser-driven plasma wake-field acceleration. I'm also joined by Professor Patrick Meade. Professor Meade is a member of the C.N. Yang Institute for Theoretical Physics at Stony Brook University. His research interests are focused on physics beyond the Standard Model and include phenomenological and theoretical aspects of new physics, such as baryogenesis, collider physics, dark matter, flavor physics, and supersymmetry. He is also deeply involved in the push for future high-energy lepton colliders, including a potential muon collider. Last, but by no means least, I'm joined by Professor Patrick Koppenburg. Professor Koppenburg is a particle physicist at NICEV Amsterdam and has been editorial board chair, physics coordinator, and operations coordinator of the LHCb experiment at the Large Hadron Collider. Currently, Professor Koppenburg is coordinating physics performance studies of potential new lepton collider concepts at CERN under the umbrella of the European Committee for Future Accelerators. So I couldn't hope for a better set of special guests to help me navigate the potential future roadmap of particle physics. So Patrick, I'm going to come straight to you because I know this is something you've done a lot of work with the report of the topical group on Higgs physics. I'm going to start with the question, why do we need new colliders? So these are complex, expensive, hard to realize machines, and there appear to be 2 major motivations: precision physics and energy reach. And the first thing that the community seems to want is precision physics and a Higgs factory. What is a Higgs factory and why do we need it? Why do we need this precision machine following on from the Large Hadron Collider?
Well, I'd say, even like the more basic point beneath Higgs factories is that certain questions about nature, we obviously want to use every possible experimental input to get at it, but the question of electric symmetry breaking in the Higgs is kind of the most pressing question that the LHC has given to us. And of course, if we had infinite precision in other experiments that weren't colliders, maybe we could gain information about it. But the way quantum field theory works is it tells us that we really need to be probing this energy scale of the Higgs to ask the questions that we want to ask. So I think that's the basic point for colliders. And then your question about Higgs factories versus others, Obviously, we'd like to understand the properties of the Higgs with more detail. And at this current juncture, Higgs factories, an E plus E minus machine, be it linear or circular, this is a technology that we have available to us, and we should exploit it and keep pushing forwards on these important scientific questions.
Yeah, I think you said in these papers that you've done that the Higgs is linked to kind of 15 out of 19 free parameters in the standard model. It's kind of a new probe of nature that we found at the LHC, isn't it? And it's something that it seems crazy not to want to study it further.
Yeah, I mean, ultimately, the Higgs, or what we understand of it in the standard model, is that it really is the origin for everything we see in the universe around us. Without the Higgs, without electric symmetry breaking, none of us would be on this call being able to talk. So, whenever you're presented with something fundamental like that, which you really have no answers to why it has the properties it has, it's clearly the next kind of goalpost that we want to go after in particle physics.
Yeah. And if we switch to the other side, the other machine that seems to, I think the community seems quite happy with the idea of a precision machine, a Higgs factory, and then the other type of machine that people might want is a higher energy machine. Why do we want to probe higher energies above the LHC? Let's say at the 10 TeV or up to 100 TeV, Patrick. What are we kind of looking with there?
Well, I mean, I think it has kind of two goals. In one sense, we're explorers and we want to probe nature at the shortest distances and try to understand nature at that level. The other side is this question of electroweak symmetry breaking. It really is a different problem than we've ever had to confront experimentally before. And although we use the same terminology like Higgs factories or other factories like B physics or Z's, the Higgs acts in a different way than any other particle we've seen. So a 10 TeV scale or any high energy scale collider offers you this ability to do exploration, but it also is necessary to unlock some key questions about the Higgs because our factories that we're proposing now are great steps, but we won't even be able to touch some of the properties of the Higgs predicted in the standard model. For instance, the properties that explain why we're here, unless we have an enormous amount of more Higgs bosons. Yeah. And since we don't have infinite power supply to make the luminosity of our colliders as much as we want, the only other lever we have is energy. And it kind of does a double duty from the quantum field theory nature of cross sections.
Excellent. So we want higher energy and we want precision, and those might not both be possible at the same machine. Right. Now, before we start getting to the specifics of particular colliders, Jenny, I want to come to you next. We'll go down the screen. Before we get into the specifics of future colliders, let's zoom out. When we're talking about future colliders, what are the key metrics that we should be looking to optimize? Because some of the people who are against new machines will say things like, people in HEP are trying to just protect their jobs or create work that needs doing. What are the key metrics that we should think about when we're looking to build these new machines?
Well, I think the key metric is clearly the scientific potential of any machine, right? And I think
this is from the scientist perspective, obviously.
From the scientist perspective, right? I think Patrick summarized it very, very neatly. Yeah, I mean, there are simply things, especially related to our existence and the history of the universe, which we can only probe with colliders with sufficient energy and luminosity. However,
then life and politics
there are more things than
yeah.
science, right? I think there is. I think if it were only science, then
we would just build them and everyone would be happy. Yeah,
exactly. Yeah, but of course, there is also realism, right? I mean, we need to have a technology to first of all do it, and then we also need to be able to pay for it, both in construction and and of course also in operation. And of course we also need to discuss how much we want to focus all the resources which a research field like particle physics can get into one single project. Yeah, and to which extent we need to balance the cost of maybe our flagship project, against what should be also they are available for doing R&D for maybe the next machine, for doing smaller scale experiments, more specific experiments, which are less general purpose, but still, do very important contributions. So I think, therefore, there is not one single measure.
Multi-dimensional.
It's really a multi-dimensional thing, and clearly at some point, there are also personal preferences and personal judgment and personal views of the world at large, and the role particle physics plays in society comes in.
But this is a really important point to make, isn't it, Jenny, that these are ongoing discussions at the moment in high energy particle physics. It's not just people saying, oh, I need to have a job. Please build this. Please build this. People are looking at this very, very seriously in terms of cost, in terms of carbon emissions, in terms of physics reach, in terms of citing these machines. These are ongoing deep discussions where people have lots of different opinions. It's not just, please build this, and this, and then we have jobs for 100 years, like some people would say. These are big ongoing discussions within the field.
Absolutely. And I think it's important that we have this discussion, and take the time to do it. And because it's a big decision to take.
Indeed. And it could lock us into things for many years to come, as we'll sort of come on to. So, Patrick, Kay, if I come down to you, let's move into the options for a precision machine after the end of the current Large Hadron Collider. What are the main options that are on the table for a Higgs factory or precision machine after the end of the Large Hadron Collider? And perhaps we can discuss the potential pros and cons of some of those machines.
Yes, so maybe we should start with CERN, because we are at the beginning of a community exercise of the update of the particle physics strategy in Europe. So obviously this will focus a lot on Europe, and the hub of particle physics in Europe is CERN. So now a lot of projects are coming, proposing new experiments to be built at CERN, or at least coordinated by CERN. So at CERN, there is the big flagship project of what I would call of the CERN management is the Future Circular Collider, the FCC, which is a 100-kilometer long tunnel that you see here in this image, where the plan is first to have an electron-positron collider that would be a Higgs factory to run for a decade or two, probably 2 decades, and then you take everything that is in the tunnel out and you put in another accelerator, which would be a hadron collider at an energy of around 100 TeV. But hadrons, that means protons. Protons always, like in the LHC, come with the problem that you're not using the whole energy to do the collision, you're only using part of that. So you would have an energy reach of about the 10 TeV that Patrick mentioned earlier. So this is the flagship project that CERN is pushing, but the community has their say and also proposing other projects. So Jenny is the leader of one project, which is a linear collider that would be put at CERN, and that would be in a straight line and parallel to the lake. And there would be an electron-positron collider also being a Higgs factory. Now you see here the image. So it's a competing project for a Higgs factory with pros and cons that we may be able to discuss later. So and then there are plenty of upgrade possibilities for that, and there are so many that I will not list them all now. We can discuss them later. That's the nice thing about a linear collider, is that you can extend it. A line doesn't have a fixed length, while a circle does have a fixed radius. So you can think about what to do with that tunnel later, but you don't need to decide now what you want to do. And then there are projects outside of Europe. There's the US, who had their similar exercise a couple of years ago, and they decided that they let Europe build an electron-positron Higgs factory that they would join, but they are not going to lead on that. And in the meantime, they'll finish their neutrino experiments that are very very expensive and also very exquisite, but that's a different kind of physics. And then they're focusing on the R&D for doing a muon collider, which is also a very exciting project, but longer timescale. And then in parallel, there's China, who have a project called CEPC that is essentially a copy of the FCC, just located in China. So same story, 100-kilometer tunnel, and first electrons, and then potentially hadrons.
Excellent. That's a wonderful overview. So maybe if I just let you go on, Patrick, because you raised the idea of the CEPC. So this seems to be the first project for a Higgs factory that could get off the ground, potentially by 2027, if it's in the Chinese 5-year plan, the next one. So what would be the positives of China going ahead with the CEPC? Why might the HEP community be happy to see this occur? What are the positives here?
I'm maybe not the right person to list the positives, of course, because in the discussion of the European strategy, among the people I've discussed with and the community gatherings I've attended, there's mostly skepticism about this project because of China. It's fantastic if such a collider is built and it's built quickly, but it's an open question of whether actually European scientists could actually join such a project, and it's the same for the US. If I'm going to China, my funding agency wouldn't let me take my computer and my phone with me over there out of fears that the Chinese government might be spying on me. So I can't imagine now working in an experiment in China. But then I can't predict of what the political climate will be in China in 10 or 20 years. That's an open question. And Europe has nothing to say about this decision. This is solely in the hands of one man, the chairman of the council in China. So we will see, and depending on the decision, we might have to react.
So I listed some potential positives, and they come with various downsides. So China is becoming very much a scientific superpower, and we have some examples of them building projects very, very quickly. So we have the Heaven's Eye telescope, the FAST telescope. Now, this comes with some downsides because they tend to relocate people in not necessarily the most ethical way to get these projects done quickly. And also, Patrick, you mentioned this, but they could kind of beat CERN to the punch, right? So this is, we could get there quicker, but this might then have knock-on effects down with CERN. Is that fair, Patrick?
Yes, but if China decides to build a circular electron-positron collider, then there's no point CERN doing the same thing, because they would be 10 years later, and it would only be a cross-check machine. Maybe then, after a very long time, the integrated luminosity, the amount of data at CERN could be higher than that of China, but that's
marginal
very
gain.
Dangerous, marginal gain, and very difficult to bet on. Then CERN would have to react by either going straight for a hadron collider, or saying, wait a second, a circular collider can't go that high in energy, not as high as a linear collider, so we could build a linear collider and go straight to an energy that CEPC wouldn't be able to reach. Or we could bet on the muon collider and join forces with the US in order to make sure that we can build a muon collider as quickly as possible. So that opens a lot of possibilities that we would need to discuss on what is the best strategy to keep the flow going, to keep the momentum in Europe, to keep the people in Europe doing the R&D, and in order to have a project that doesn't come that long after the end of the LHC, that's still supposed to run until the 2040s.
Yeah, and we're gonna move into those points. So, from the kind of positive point of view, it would be built quickly. It could do some really, really good precision physics, but on the negative sides, this comes with potential some shady practices, as we might see it in Europe, and also knock-ons would European scientists even be able to get over there? Would the data flow freely? What are the political tensions going to be? So there are pros and cons to this. So maybe if we move over to the the other side then, let's move over to Europe then. So Patrick, if I come back to you, what about the FCC EE? What are the big positives of this machine rather than the Chinese machine? Why should we be, and many people are, very, very positive about building this precision machine at CERN instead?
Well, I guess it depends on which angle you want to come from. I mean, obviously, as we've just discussed, there's the geopolitical aspect of this and the openness of science. I mean, as a theorist, since I'm not going to be working on any experiment or building any accelerator, I personally think CPC would be an unequivocal win scientifically, in the sense that
I think European funders probably think it would be as well, right? Because they don't then have to fund
potentially. But then in terms of what you can actually kind of view this in terms of, if you build FCC or have a very clear direction for where Europe is going, that's kind of the impetus to actually start building something. Right now, when there's all this indecision and what projects are we going for, it kind of feels like we're in this sort of weird twilight zone where we know we have a target in particle physics. The question is, how do we move there? So
is that contingent? Do you feel like, because you flagged that up, do you think people are waiting to see what China does, which is kind of something that is going to come soon? Are we just in a sort of holding pattern, waiting to see what they do?
I think everybody has their own personal take on this, but I mean, certainly if you have informal conversations at coffee breaks or with your colleagues, everybody is kind of doing this sort of dance about who's going to do what. And I mean, this isn't the first time we've experienced this either. The community for the last decade or so has been doing this with the ILC as well. I mean, we've had a Higgs factory ready to go with the TDR for more than 10 years now. And
I see Jenny nodding very much. Don't worry, Jenny. We're going to come to you on the linears next. Don't worry.
I mean, yeah, I mean, it's really kind of, I mean, some people will joke as a zombie project. Some people will have other words for it, but this is something that's been in the community for, I mean, looking back to Snowmass 1982 or 1983, whatever the first one was, a linear collider reaching energies of a TeV was actually proposed more than 40 years ago. And so this is one of these things where the field is very used to now having this uncertainty about what project goes forward. So I think whether China moves forward with CPC or whether Europe comes strongly with an FCC or linear collider, I think the real question is, the real benefit of FCC, which was the original question, is if CERN decides to go forwards, it's a strong direction for the field that we actually are making progress on, rather than spending all of our time planning on the options.
And I guess this, Patrick, is a very mature technology, right? So CERN would be playing the same game it played with the Large Electron Positron and then LHC. It would be repeating it with higher energies and playing the same trick again. It's something that they would understand how to do, and would also provide a long-term vision, as you say, for CERN.
Yeah, I think both with linear E plus E minus and circular E plus E minus, it's kind of well-established technologies that accelerator physicists know how to do, and it lets us start addressing some of these questions. It might not finish addressing these questions, which is where we have these high energy aspirations, but the FCC EE would be a clear direction that would provide infrastructure for the future. And that's, I think, one of the most positive aspects to it.
And the big negative is that China can sort of eat your lunch and do it cheaper, I guess, is the idea, right?
Yeah, I mean, that's the ultimate question of how much more quickly China could actually make this work and how it positions other regions. I mean, I think geopolitically, the nice thing to think about this is, historically, we've had colliders in the US and in Europe, and that's kind of been dominating the landscape. Obviously, if China were to enter in, yes, it brings a lot of confusion for Europe and the US as to what to do.
But it brings another player, and
the benefit would be another major scientific superpower deciding colliders are something that is really particularly interesting. So that's a pro and a con, depending on what region you're talking about.
Exactly. So Jenny, I'm going to come to you because I saw you getting energized when we were talking about the linear collider. So another option for one of these Higgs factories is a linear collider, potentially at CERN. There's been talk of it potentially in Japan over the years. I know Mark Thompson, who is the current DG at CERN, was on a lot of those linear collider sort of panels, at least when I was in Cambridge. What are the positives of building potentially a linear collider at CERN instead of going to this FCC-EE? We go to a linear EE collider. What are the positives there do you see over the FCC-EE?
Well, I mean, for me, the most important positive is that you can actually reach much higher energies in E plus E minus collisions. And that's important because electrons and positrons are really elementary particles. So when they collide, they really annihilate, creating much cleaner conditions than at a high energy hadron collider. And there are many important physics processes which one would want to look at in E plus E minus collisions, but which are not reachable when you are limited to even a huge circular E plus E minus collider like FCCE.
I think you mentioned they could go after, for example, producing multiple Higgs, which is something that the FCCEE would not be capable of doing because of the synchrotron radiation. But yeah, you could do a little bit of a mashup between a precision machine and energy reach with this linear machine.
Exactly. It combines, you can have a much larger range to look for sort of direct production of new particles, but also for studying the top quark, which is really a big mystery. I mean, that's a quark, a sister of what is the constituents of a proton or neutron, but it as a single particle weighs 175 times as much as a proton, and is even heavier as the Higgs boson, right? So if we're honest, we understand very little about the top quark and how it must have a very strong relation to the Higgs and maybe also to how the whole complicated hierarchy of fermion masses comes about, which we also don't understand. So, and there are many measurements about top quarks and their in particular their couplings to the electroweak gauge bosons, which really require high energy and also a control of the chirality of the colliding particles. So I think that's, in short, the scientific advantage. There's also a mix of strategic and scientific, because I think what we should also not forget is that the LHC has still a very, very rich program ahead. And it has only seen a minor, in some sense, a small fraction of the data it is supposed to take until the early 40s. And I mean, there are really good chances that it still discovers something, right? And how do we react to this? We talked a lot about how we react to China building something, but
is there more flexibility here with the linear collider? Is that kind of what you're trying to get to?
Yes, exactly. I think we mentioned this already when we discussed competition with China, but I think the strategic advantage of a linear collider is you can build a rather small version of it to just do a minimal Higgs precision program, which would be cheaper than building the FCC, so it leaves you more freedom to do R&D for your muon collider, or by the way also for the high field magnets which you would need for a new hadron collider. So I think we also didn't touch on that one yet. I mean, we are lacking the technology for say the second step of the FCC program today in a way that it's affordable and sustainable. So in that sense, the flexibility is then to say, okay, be it that LHC discovers something which we want to see, or that simply China is faster to do the basic Higgs program. We would sort of directly go to higher energies with the linear collider. And you can do this in two different ways. There is sort of the guaranteed way to say you take today's technology and just make your tunnel longer. That's what is sort of the color different orange, red, yellow colors on your picture indicated. However, what we developed over the last years are also say a perspective where we say, hey, wait a second, why don't we simply stick with the same tunnel length but put in better technology?
Yeah.
And I think there, of course, the point is, I mean, I personally think sometimes we are a bit stuck because on one hand we need something which is very mature and industrialized, and before you can really build such large things. But at a time you do this if you want for scientists, maybe, who are not engineers and technicians and maybe boring part, people come up with new smart ideas. So then you say, oh, there is something better. But you don't realize that this again will take, of course, many, many years until it's really ready that you can building a large scale project with it. And what I realized over the last year is that really such a linear facility could be the way out of this dilemma. We can use the technology which we have in hand today, and which we have other linear machines running here. For instance, here in Hamburg as an X-ray laser and so on. But also, at SLAC in the US, and China is building such a thing. So you can do something with technology you understand, but you have a clear perspective how to bring in in the years to come all the bright ideas which are under development now, and where you don't know at the moment which idea will make the race in the end.
So you could bring in, for example, keep the same tunnel and use your plasma Wakefield acceleration or whatever it might be. And you have this flexibility. So this allows flexibility in terms of the scientific program and also in terms of the technologies coming online. I guess it would be cheaper than building the FCC EE. Jenny, is that fair?
This depends, of course, on the energy you want to go to. I mean, I don't know the most recent numbers for FCC. I don't know when they will be public. But what we will put in for the European strategy is that say an absolute minimal version of a linear collider at CERN would be something like around 7 billion Swiss francs. What a bit more comfortable thing with a bit longer tunnel and some other nice features would then be at 8 billion. But if you wanted to say have really the maximum we are talking about, this would bring you also to 13, 14 billion Swiss francs.
Okay. So still an expensive project.
So this is all still expensive, right? But there is a lot of choice. You can, there's basically a factor 2. If you go through the numbers I mentioned, there is a span of a factor of 2, where I think first of all, the community has to discuss, what really the priorities are and what to bet on. But then, of course, this also gives you contingency in both directions, right?
So potentially cheaper, very much more flexible in terms of technologies you could use and the scientific program. And this could this sit alongside neatly with a Chinese program if they go ahead with the CEPC?
I think so.
Okay.
I think so. Of course, you would want to invest then more. So I guess the very cheapest version I guess then, at the end, this is then also really a political decision whether Europe will be, wants to stay a major player in this field. If China really goes ahead with this project, as we said already, they will really become a huge scientific player. And I think it's in the end of the day, I think it would be really good to have to have also in Asia, a big scientific hub like this, because if particle physics becomes something which is only happening at CERN, then maybe also the global interest is hard to be maintained. Yeah, so I think despite the political differences and complications at the moment, which Patrick mentioned, I think in the end for science it would be good if CPC went ahead.
Yeah. So I'll come to you, Patrick. What do you see as the potential, any negative or downsides of having the CERN linear collider? I know you have done a lot of work on this. The thing that has always been thrown at these machines, that from when I was studying these, has been the luminosity argument. You can't get enough luminosity, that the circular is the way to go. Any thoughts on that, Patrick, or any other potential downsides of building a linear collider at CERN instead of the FCCEE?
Yes, so the plot you're showing is the one argument in favor of circular collider, and the interpretation of this plot depends a lot on which region of the x-axis is most interesting to you.
Yeah.
There are people who absolutely want to run for 3 years at the Z boson and have a sample that would be 1 million times larger than what was collected at LEP in the 90s.
The TerraZ project, I think.
The TerraZ project, and there's fantastic things you can do with that, that would also allow you to do, then it's precision measurements at the Z, and that would also give you access to very high energy scales just by the interference of these high energy scales with the Z. So there are people who, and this is a program that you wouldn't get in the same extent at the linear collider, because it would be a waste to run for a long time at the Z at the linear collider. And then as you go up in energy, then the linear collider starts to take over. So it's really a question of betting of where you expect most of the science to be relevant.
So this is kind of what Jenny was saying, right? If China goes down here and CERN goes up here, then that's kind of a nice separation of work.
Yeah, that's one thing. Then there are many people in the field who actually want to continue doing proton collisions. They were very fond of the LHC program, and they just want to continue that program at the higher energy.
Yeah.
And to do that, they need FCCHH. Yeah. So for FCCHH, there's no question you need the 100-kilometer tunnel. So then of course,
what are you going to put in it until
exactly? Yeah. And then since you cannot put FCCHH straight away in because we don't have the technology, as Jenny said, you first put in a circular electron-positron collider while doing the work on the magnets before you can do the FCCHH. Yeah. So if your real focus is FCCHH, then you would do that. Of course, there again, it's a question of betting, because it might be that by the time you're able to do FCCHH in 2070, you can build a muon collider, or you can build a plasma wet field accelerator. And so we just don't know. It's betting on long-term future. I'm in the camp of the people who want flexibility, because I feel a bit uneasy about deciding now on the physics research program of our grandchildren.
Yeah. And this is where I was going to move to next. So if we move into the kind of high energy stuff, so it seems like, well, Patrick, you kind of summed it up quite nicely there. So the main players here for getting to very high energy seem to be the FCCHH, or if I can find my next thing, the muon collider. So these seem to be the two choices. So what are the positives? Patrick, I'll stay with you, Patrick K, for the first one. What are the positive arguments in favor of the FCCHH then? Is this just CERN knows how to do it, it's bigger, it gives long-term stability to CERN? What's the idea here?
Well, the idea is what Patrick M said at the beginning, is that you reach the high energy scales and you create an amazing amount of Higgs bosons that are much larger than what you could do with the other projects. It is a hadron collider, so it has the drawbacks of the LHC, that you have a very dirty environment, and that you first need to fish these H bosons out of the mess produced by proton-proton collisions. But we know how to do that. At the LHC collision, we've been able to do that successfully. So a lot of people are thinking, well, let's just continue. and this is certainly I wouldn't have any doubts that by 2070 we know how to do that, or by 2050 when we start building and designing the thing. So this is indeed, it's a project that can be done and has a very clear and high scientific interest.
But the negatives are kind of what Jenny said, right? So this is a huge cost. You're kind of locking yourself into the FCC program for kind of 50 to 70 years. You're continuing this kind of strategy, which is kind of building larger and larger machines, which eventually is going to run up against the kind of technological and economic and geographical buffers. These are the big downsides, right, of the FCCHH. You're locking yourself into a program for many, many decades, when maybe when you get to 2070, the technology is completely different.
Yeah, yes, that's basically the problem. There's there of course, we haven't mentioned the CERN budget yet, but the CERN has a difference compared to China or the US, when CERN has a budget that is flowing from the member states, that is about €1 billion per year, order of magnitude, that of course they're using now completely, almost fully, to run the LHC and pay the people who are running on, who are letting the accelerator run. The experiments are mostly done by the university, so that's it's a different budget. But whatever fits in that envelope that CERN is getting is kind of within what CERN can decide. And then when you're building a big project that costs 10 billions or more, then you need to find money elsewhere, and that's where the difficulty starts. So of course, the cheaper your project is, the better it will fit in that envelope, and so you're less sensitive to geopolitical problems or economic problems that might affect the member states, and that makes them nowadays less likely to throw in more money than what they're already doing every year for getting CERN to run.
So the FCCHH, currently we can't build it because the magnets aren't ready. It locks us into a very, very long-term project where the technologies could change. What's another potential downside, Patrick? Will China, I don't know if there's any information on this, if they go ahead with their CEPC, the FCCEE essentially alternative, do they have any desire to then go to a hadron machine, or has there been no kind of discussion of that? I don't know if they have the expertise over there to do that, but I guess people would move over and help them do it if they decided to go that way.
It's the same as for FCC. They copied the whole plan. So so they also have a proposal for running a hadron machine in that in that tunnel, and with similar capabilities as FCC. The last time I looked at it, they seem to be talking of a slightly lower energy, but anyway, there are large uncertainties on this, whether it's 100 TeV or 90 or 80. At this point, we don't really know. That depends a lot on the magnet technology, magnets which we don't have.
Okay, so difficult to do at the moment with the magnet technology. Locks us into a very, very long-term project where the technologies might change. Yeah. So the alternative, Patrick M., of course, we come to you on this. I know you're a big fan when I can find it, is the muon collider. What are the positives of potentially pouring money into R&D for this project and working towards that instead of an FCCHH in 2070?
Well, I think one of the real questions that we've had, that we've kind of been circling around this resource question, and as Jenny was saying, in terms of with linear collider, you could have the tunnel and build other things in it. Ultimately, particle physics will have to change technologies in some way. We can't just keep getting bigger and bigger and bigger. I mean, Fermi had this idea of the globotron that could go around the entire circumference of the Earth, but unless we have some huge influx of funds, we have to figure out how to do particle physics in new ways. And so what the muon collider represents is a way to take us both in the directions of energy and precision at the same time, but do it in a much smaller package than we do with hadron colliders. And that's also the aspirations of what Plasma Wakefield has. The reason why I personally have spent more time on the muon collider side is that, yes, there are challenges with the muon collider, but once you actually can create the muon beam to start with, the rest of it is actually relatively straightforward accelerator technology. So in terms of what the Laboratory Directors Group roadmap laid out in Europe in the 2020s, and a similar response came from the US SNOMAS and P5 process, is that it's believed that the muon collider technology is a lot sooner than the plasma Wakefield technology. So yeah, I mean, my perspective is I think we really do need this kind of large energy jump. I mean, the technology to do precision physics is now, and we should take advantage of it. But even if you kind of get rid of the explorer motivation, which really motivates me, if we're asking about these questions about why did electroweak symmetry breaking happen and why are we here, we would really like to access the part of the universe where we actually see the simplicity of the standard model. We would like to see where electroweak symmetry is actually realized. Right now, we believe it's the standard model, and we're testing it kind of at the electroweak scale. But if you actually wanted to say, why does electroweak symmetry breaking happen? We'd like to be able to access energies significantly above where electroweak symmetry breaking occurs. You would like to see the underlying simplicity. So we need to get to this much higher energy scale than current E plus E minus colliders, whether it's linear or circular, can access. So having any machine that can get there, whether it's a PP machine, a muon collider, or a Wakefield machine, that's all different options. But from the muon collider perspective, it's a way to say it's something that we can go after in the kind of nearer term if we have the R&D investment. And it really could let us kind of change the paradigm for particle physics. It's something we've never done before. And it would let us, it's not kind of the last muon collider. It would be a first step in having this new technology that any region could go after in principle.
So instead of just rerunning this EEHH, we can now move to a new paradigm, make these machines smaller. We can do precision work and high energy work at the same time, a new paradigm, like you said. And in terms of the positive, Patrick, and Patrick K mentioned this earlier, the US at the moment is doing a hell of a lot of neutrino physics. And I know in the piece you did on the muon collider, there's huge synergies between creating intense neutrino beams and creating intense muon beams. So there are some potential synergies to be working on the R&D in the US at the moment, are there not?
Yeah, I mean, the original ideas for this kind of 20 years ago were the Project X at Fermilab, where you'd have this whole series of making this intense muon beam for muon collider lets you create a very intense neutrino beam, which would realize a so-called neutrino factory. We have these long baseline programs right now for neutrino physics, but the beams, although they're great beams for the technology we can do right now, they have a lot of uncertainty about what is the exact neutrino content in there, how collimated in energy these beams are. So this would give you a whole sort of project that goes beyond just collider physics. Yeah. And an interesting thing about thinking about new technologies and doing things we've never done before, like other aspects of this that we're actually just really touching on the physics side, where you have the neutrino factories that come along with this, but also if you have a very high energy muon collider, you have very high energy neutrino beams. And so you could run auxiliary experiments off of this, where you could have a sort of a fixed target neutrino DIS that can inform other experiments like IceCube and some of these very large neutrino telescope arrays. So there really is a lot of physics associated with choosing this new type of technology. And some of it we're actually just exploring right now, because since we've never done it, a lot of experimentalists and theorists first ask the questions we've always asked with colliders. But when you have new technologies, you can actually ask different questions and realize all these other ancillary benefits. So it's part of the excitement of the last 5 years or so, starting with the last European strategy, moving into SNOMAS with muon colliders, that we're really learning all these new things you could do, you never could do with E plus E minus or PP machines.
And there's also been, I think, Patrick, this is fair to say, some excitement from kind of younger researchers as well. If you don't have a leap in energy until kind of 2070, that's potentially not very inspiring to a lot of younger researchers. So the idea of being able to go to higher energy in the next sort of few decades would be potentially valuable to keeping people in the field. Is that a fair perspective, do you think?
I think it's a fair perspective. I mean, I think people coming into the field always want to kind of make their own way in the field and discover their things. And as Patrick K mentioned, I mean, it's very hard to set a course of action that's essentially telling our great grandchildren what they're going to be working on when we have no idea what the world will look like 50 years from now. So having some of these new technologies to work on that could bring this time horizon from the 2070s to the 2040s and the 2050s really is something that excites young people because they feel like they have an agency over what are the scientific questions they can ask. I mean, sometimes people put this derisively that, oh, young people just want to have their chance to work on it. But I think it really is more about the questions of developing new technologies and answering the scientific questions rather than just
I want to be the one who works at the shiny big machine. No, I totally understand. Okay, good. So we've talked about some of the positives and negatives of these potential future machines. Now, this was the genesis of this discussion. I put this out on X a few weeks ago. Patrick K commented on it. My blue block is getting rid of loads of people as we talk, but never mind. And I outlined a potential future for particle physics, which was China building the CEPC, doing a lot of precision work, Higgs widths, mass, couplings, CERN going straight to the FCC-HH as soon as the magnets are viable, and then doing studies of electroweak symmetry breaking, di-Higgs work, and the US continuing its neutrino program and using the synergies to push for a muon collider. Now, who's up next? Jenny, what do you think about this idea? Are there problems with this potential future of particle physics? Or is this a dream scenario? What are your thoughts here?
Well, my thoughts are that this put here on your list, you put for CERN something up where we today have no way to say whether we can build this, when we will be able to build this, what it would cost. And I think that is not what scientists in Europe like so much, and what gives them really a clear way forward, right? I think Europe and the US have identified the precision Higgs program, at an E+ E- machine as their highest priority in particle physics, and leaving that completely, to a country where we are all not sure whether even if we wanted to, we could participate. This for me does not, fulfill the scientific requirements which we all have put forward.
So this is me naively wanting to optimize, but we have to be careful about the interaction politically.
Not long ago, we had a similar plan where you could replace the CPC in China with ILC in Japan. So I think there is a lot of value in actually coming to a global agreement who does what, because our research is incredibly expensive and and we rely on the fact that we build huge machines which we can only build once in the world. So in that sense, we might need, despite the luxury situation that CERN has, this significant budget, which we discussed. Also Europe might need to at some point, participate there in a more global approach to sharing the load of all these projects. And I think with Japan, this would have worked out nicely. But to cut a long story short, it didn't, right? So, but I think we cannot, I think we cannot just say we leave all the wisdom of Higgs precision physics, which we all think is our highest priority, to China.
So I'll stay with you, Jenny, then. So maybe if we move off my naive suggestion, which got a lot of talking going anyway, if we talk about these machines, then what would be your dream scenario for what machines get built? A rough sort of timeline going forward into the future. What if you had control of all these countries? You had control of all their budgets. You had control of the entire workforce. What would you be building? How would you be optimizing? What would you like to see as the kind of future over the next sort of several decades? And I'm going to come to everyone and ask this.
Well, I think in a complete dream scenario, a country, which has the resources and the know-how and is a democratic country, comes forward and picks up, the idea to build at least one of the cheaper versions of a linear collider. Because this could be, this could potentially still be faster than at CERN, because CERN simply has still the high luminosity LHC program to conclude, right? So, because then, but I think this physics needs to be done, and I think doing this in a flexible way, which does not lock us in for a whole century into one plan, but doing it stepwise, starting with something affordable, see what happens, and then decide on the next step, again taking all the advances in technology and also scientific discoveries and whatever into account. This is my dream scenario, and I think we need to and I think at the moment, there is no other obvious place to build a new collider for the Higgs apart from CERN and China. The US said no thanks. And Japan sort of said nothing, which everybody takes as a no thanks.
So what's sort of coming through very strongly for you, Jenna, is we need this flexibility. If we're going to build something at CERN, we need to have flexibility to be able to react when China does something, when new technologies come along. It's dangerous to put ourselves into a project which is going to be 60, 70 years with a very firm sort of lock-in.
It's not my approach, right? I think other people think that having a very long-term plan gives them security. I think I can on an abstract level understand that. But I think that's not how science should be.
Patrick K., do you want to add on to that?
I would like to add on to that of course now we're focusing on the high energy machines, but there are also other smaller accelerators that are running, and they're doing a very important physics program in Japan with the B factory, in Beijing with the CHARM factory. And there are also plans to upgrade those and do precision physics that is important and also brings input into the understanding of the standard model, but also input into pinpointing some of the parameters that are then used in Higgs physics and high energy physics. So the program is a little bit broader than the few accelerators you mentioned.
Of course.
Of course, what we need is a Higgs factory. What we need is show that we can build a muon collider, because in long term that's probably where we want to go, or show that we can do a plasma collider, whatever brings us to very high energies. And if we can't get any of those, then we need a hadron collider. I'm not completely sure whether there is actually a physics motivation for a hadron collider, even in parallel with a muon collider. But I'm sure that there are people who would think about that, and then indeed distribute these over the world. We are the three of us. We're from a generation where we've known that there was this fantastic situation where everybody was coming to LEP in the 90s, and then there was Tevatron running in the years 2000 in parallel with Bobar and Bell doing B physics, and then the LHC came up, and people were going to one country, designing the experiment in one country, doing measurement in another, kind of freely. Today it's getting...
Now the timelines are stretching out.
The timelines are stretching out, and it's difficult to get to China, and it becomes increasingly difficult to get to the US as well. And so so we are facing uncertain situation, but I hope that this is not something that will last for decades, and that we can go back to more international collaboration. So maybe the dream scenario is more international collaboration and more freedom to do research wherever there is facility available.
Patrick M., do you want to add anything to that?
Well, I mean, I think when you say the dream scenario, I mean, you have to at least give me some variable that I'm optimizing over.
So, okay, yes, that is a very fair.
mean,
So
obviously one dream
maximizing
scenario-
physics reach, let's say. What would we
Yeah,
what would we look at?
I mean, one dream scenario could be that if China goes ahead with CPC, and I forget about global concerns, then we can imagine that a correlated program between Europe and the US with muon collider R&D can bring the time scale up, and then CERN could go directly to a muon collider right after the high Lumia LHC. Yeah. Because one thing that we've talked about with flexibility, right? We've said, well, if you build a very large circular tunnel, you lock yourself in for a long time, but you have many options to put in the tunnel. You can put the E plus E minus collider to start with. You can put a low energy HH. Yeah. You can put maybe a muon collider in that tunnel. But there are other, and then the linear collider, we said, okay, well, we have the technology. We can make it now. You could extend it with kind of click technology to 3 TeV or so, or you could go to high energies. But depending on how you optimize for your dream scenario, yet third option would be to say, well, let's build no new tunnels for right now. And you could do LEP3 in the LHC tunnel to access the Terra-Z program and a lot of the Higgs program. And then what the International Muon Collider Collaboration is looking into is actually reusing all of the tunnels at CERN to be the accelerator ring. And then you just build one smaller tunnel on the CERN campus for the Muon Collider ring. So there's really many different directions we can go. It really comes down to what is the cost envelope and how do we maximize R&D versus some of the smaller projects, like as Patrick K said, like this is not the only game in town for physics, and what the other various regions of the world do. So I can come up with multiple dream scenarios. You just kind of give me some box of what I'm dreaming inside of.
Well, so it's interesting. So obviously there's a hell of a lot of politics involved in the decisions to build these new expensive high energy colliders. You know, there's workplace concerns, economic concerns, geographical concerns, physics reach concerns, carbon emissions based concerns, and many, many more. So given that deciding on which machines to build, if any, is so difficult, do you think it's fair? I'll stay with you, Patrick M. Do you think CERN's kind of full-throated support of the FCC program at the moment is kind of a little bit premature? Is this more CERN kind of trying to secure its future rather than necessarily listening to the community as much as it needs to? I know that's kind of a loaded question.
Yeah, especially for someone not at CERN.
Okay, fine. All right, we'll come back to you, Patrick. We'll go to Patrick K. Has CERN listened enough to the community? Has a community consensus arrived where we can be asking people to line up behind the FCC full program? It doesn't sound very much like it has.
No, not yet.
Okay.
And that what CERN management is doing is they are implementing the decision of the previous European strategy, which was one of the decision was to do a feasibility study for the FCC, and now they're doing that and they're communicating a lot around that. And so a lot of people have the impression, oh yeah, this is CERN's project and this is CERN's future. Well, CERN's future is whatever this strategy update is going to decide. What's the
timescale there, Patrick? Is that when's the next strategy?
So the strategy, we are meeting in June in Venice to discuss all the options. Then there's a group of selected people who will write a report for the CERN Council. And then the CERN Council will come with a decision either in March or June 26. So we're discussing on this timescale. in a year or so from now, we should know much more. Yeah. And then what I'm hoping is that whatever is decided there, the community will unite and join this project. I'm sure there are some people who are so dogmatic about shapes of accelerator that they would never join an accelerator that doesn't come with the right topology. But
so it's right to be trying to get people united, because united projects get funding, but you have to have a consensus first within the community that everyone can unite behind, and we're not quite there yet.
And it's clear that as soon as there's a decision, I will join whatever is decided, because I want to build a detector at the Higgs factory and then analyze the data. Although I'll probably be retired by the time this data comes. But now we are discussing, and which gives a little bit the feeling that the particle physics community is not united and doesn't know what they're doing. It's just that we have plenty of very good projects and too many to be built. So we need to reach a decision somehow.
Mm-hmm. Jenny, do you think that people kind of, and maybe this is because, united groups are more likely to get funding. Do you think people feel a little bit pressured at the moment to endorse the FCC program? It does seem to be the only game in town when you look on the CERN website. Obviously, there are links for other projects, but it does seem to be, this is where we're going, this is where we're heading.
Yeah, I think, the majority of particle physicists is very conscious that they have a huge responsibility there also, right? Because I think in the end, I think everybody knows and agrees that in the end we have to converge on something and unite behind this. I fully agree there with Patrick. Yeah, and but I think there have been different views on how far we are in this discussion, right? I think it's very good that CERN did this feasibility study for the FCC. Yeah, this was what it should do. Although I think the last strategy mainly said for the Hadron Collider. Yeah, but nevertheless, yeah. But I think it's important to see what really the actual costs and implications are, and then we all have to discuss. Yeah, and come to a conclusion, and I think that's it.
So it sounds like the next year is going to be pretty huge, right? We have the strategy coming out. We have, I think China's next 5-year plan is somewhere in the works. I'm not sure exactly of the timeline of that, but it's I think they make a decision soon. So it does feel like the next year is an incredibly pivotal time, Jenny.
At least it will be an exciting year.
They say, may you live in interesting times. Yeah.
Yes.
I guess we said too often that the next year will be the year. Yeah, but it will definitely be a very exciting year.
There was an interesting, where are we? There was an interesting piece that came out a couple of weeks ago. See if I can find it now. Where did I put it? Maybe I had it. Came from David Castelvecchi, where he was talking about, let's just leave it on here. I'll come to you, Patrick M., where he was talking about the end of the LHC. So Jenny and Patrick have flagged up that the LHC still has a long time to run. So until the 2040s. I've got the timescale somewhere, if I can find it. There we go. Yes, his piece here. It was the biggest machine in science inside the fight to build the next giant collider. And in there was some quite prominent voices in the field who mentioned the end of the LHC program, and they suggested a couple of ways we could go. And one of them was essentially running the LHC into the ground, because it's the only high energy machine we'll have for a while, and doing a lot more Higgs potential di-Higgs work. What do you make of that idea, Patrick M., running the LHC longer than is scheduled at the moment to do more di-Higgs work, more potential work?
I think there's the question of, you hit a point of diminishing returns. I think the real question, though, that has to be coupled to that is what investment in another technology you've made to what is another option to getting to high energy. Obviously, if we don't have anything on the table to access this energy scale or that's financially affordable, then that certainly is an option. But at the same time, I think in that article, and people have also discussed about like, what if you
Cutting
don't do the
short.
full high luminosity LED run and save some money and invest it in other directions? So I mean, I think that's the real question, that something has to be coupled to the axes of what is the actual costs available, the resources available, and how much the other technologies have progressed. I mean, because even the end of the high Lumi LHC, we say like this is the program on the books. That's a really long time, right? I mean, we're talking May 40s right now. And I coming back to when I kind of skipped the CERN question earlier and let the
that's all right. It's perfectly reasonable to do so. I realized as soon as I asked, I was like, I'm putting him in a bit of a tight bind here. So
I mean, I would say that the US can give two kind of lessons from this perspective, or maybe cautionary tales, and one of them. One is, if you look at the last P5 process, so we have a community process.
Is it this one, Patrick, by any chance?
Well, I wasn't actually going to go to that.
Okay, all right, that's fine. I just wanted to. I'm just teasing you. I'm going to go back.
But one interesting thing to think about the strategy processes is if you look 10 years ago in the US to the previous strategy process, it had an entirely different outcome in some sense. The US was getting out of collider physics. The muon accelerator program was completely killed off. And then you pass forward 10 years, if the community puts a lot of work in and doesn't just say, okay, you tell us what to do, we essentially change course entirely in the US from that perspective. Obviously not in the existing projects like Dune, that's still the flagship and the emphasis of the US. But in terms of our collider physics perspective, things have changed a lot. So I don't think the European strategy process is a foregone conclusion, and it has kind of a different structure than the US, where our process of snowmass to P5, like the one outlined in terms of European strategy to CERN Council, our process, P5, actually has budget envelopes of what they have to fit in. The European strategy process doesn't have budget envelopes. And then it's the next layer of CERN Council that has to decide what they can afford. So it's very kind of different ways about going about that. But at least the US has provided an example where you can change direction. The other side, I think, which is an important lesson, it comes down to these machines. And the US over the last 20 years or so has spent, I mean, it's also on the order of $1 billion US per year in terms of the program, so similar to CERN. But we've spent a lot of money on projects. And when you spend all of your money on projects, there's a lot less money that can go to research and a lot less money that can go into R&D for new technologies. And so I think that's also a nice cautionary tale for Europe to say that, yes, the US is still doing great science, but part of the reason why we can't directly go to new technologies is we've not been spending a lot of money on the new technologies. And so depending upon what project comes out of European strategy and CERN Council, yes, CERN Council might say we can afford project X, but the question is, does that need money so that our children and our grandchildren have new technologies they can play with?
I mean, I think the word that has come out of this from everyone is kind of flexibility, particularly over the next year where we don't know what China is doing. We don't necessarily know where the US will want to go. We need that flexibility going forwards, right? And we need more discussions within the community to do this. Patrick K, do you have any thoughts on the potentially changing the end of the LHC running, or is that something that we need to discuss over the next year?
And this is something that regularly comes up in either direction. There has already been a change in the sense that what you're showing here is the latest timetable. Before that, there was a 1 year break between what was called Run 5 and Run 6. So they've already realized that they don't need that, and that and they merged it and therefore made the program 1 year shorter. There are of course CERN have their budget constraints, and they could say, well, maybe if we save a year of LHC, we free some budget. But there are also all the funding agencies that have been building detectors and who are still upgrading detectors Atlas CMS, LHCb, and ALICE, they have major upgrades still in the pipeline that are not yet approved that would be implemented in the last technical stop. And if you tell them now that we're going to make the program shorter, then that completely changes the plan, and there's a lot of wasted effort then. And also in the other direction, if you want to make it longer, then you wonder whether these detectors are actually able to sustain the integrated radiation and so on, or whether you need to upgrade them again. Which again, it costs a lot of money. So it's a question of, it's not an adjustment variable that you can easily change. It's something that you would also need to decide now if there's a major change, and then you would need to say why you're making this change, and everybody has to agree on that there's good reason for making a change to the program.
So you would need to run a lot longer, right, to make a visible impact. Yeah,
this is what Patrick M was saying about diminishing returns, right? If you're just going to keep running, it's pointless. Which would again take away possibilities to invest in new things, right? Yeah, indeed. Right. So let's get to the end of this. I've kept you for a long time. So what I want to leave people with is, what are the next step forward? The next steps forward. When will we get clarity on what the movement forward is? So Patrick K, maybe if I come to you, when will we know much more? You kind of flagged up the summer of 2026. Why will we know much more about what the future of particle physics will look like then? What's going on between now and then to give us more clarity?
Well, that's what the plans of the community update are. It's that we're putting the input this year, and then in 26, CERN Council decides. And I hope that by the mid of 26, they'll come up with a decision that could either be, okay, we're building FCC, or we are starting the feasibility for a linear collider, with the understanding that then the linear collider would be the project. If the outcome is we don't know what's going on, we need to reflect further, then that means that the process has been a failure. So
Patrick, did Varvar get to you yesterday? Because he messaged me and said, please make sure out of your discussion tomorrow that it is very clear that whatever the decision is, we need to make up our bloody mind and then get behind it, right? So there is a lot of time for discussion this year, but then we really need to kind of line up and get on with it, because at the moment there's just a hell of a lot of uncertainty. That leaves space for people to say things like, particle physics is dying, nobody knows what they're doing, CERN is just trying to keep jobs for people. All these kind of things go out into the ether. So there's room for discussion now, and there needs to be a consensus building within the community. But then in the next year, we really need to kind of form up behind an idea, right?
Yes, and then I'd like to zoom out a little bit. We've discussed the science, so the reason we're doing that is science, and one of the outputs of our research is the science that goes into textbooks and shows how the Higgs potential looks like, and so on. What we're also producing are PhD theses and students who get trained, and postdocs who get trained, the majority of whom don't stay in the field, but then get jobs elsewhere. And these people are useful for the economy. Otherwise, they wouldn't get jobs. The majority of the people are people like you, Sam, who then do something completely different after having done a PhD on CP violation and D mesons. So that's also an output. And then there's the output of the technology that we are building experiments very often based on technology that doesn't exist, but that we know will exist by the time that the experiment is assembled, and that forces us to do R&D that is done jointly with private companies that then get a return in know-how, and all of that is probably what our funders want, and it may well be that the shape of the Higgs potential is what they care the least about. But what they want is that we continue doing the nice job we're doing.
A load of people do AI to find di-Higgs events, and then they end up in some company down the road. But
yes, for instance, yes, that's one of the things we're doing. Or people who are working on electronics and then end up making faster, smaller, and more efficient computers, whatever. So this is the output what we're doing, and the input that's the amount of money that we're getting from the funding agencies, and that's the amount of energy that we're using. We've also slightly touched upon that, but of course it's also a time when it's difficult to justify that we're building a machine that consumes as much electricity as a small town, and there we also have to think about how we build our experiments, how flexible we are. It's again about flexibility, about whether we're able to adapt to the amount of electricity that is available quickly, and these kind of questions they're also coming up.
So closing remarks then. What do we need to get done as a community over the next year? Jenny, I'll come to you first. What do we need to aim to do to make sure we go forward in a sensible, optimized way as a high energy physics community? What needs to happen over the next year? Final question.
Yeah, I think we really have to have an open-minded and fair and scientific discussion among all the whole particle physics community, without prejudices, and really to our best knowledge, come up with a viable plan for CERN, and maybe even see this in a more global context.
Makes sense. Patrick M., what do we need to get done over the next year? Anything to add to that?
I mean, I think just echoing what's been said, I think we just have to actually come up with a specific plan to go forwards, because obviously the US and China are very large economies and they can do colliders in these regions, but CERN is actually kind of like the one unique place where having roughly a stable budget lets you make these plans. Like, we can have aspirations for a muon collider in the US, but we have no guarantee. I mean, like, our budgets are year to year, right? They could change dramatically depending upon...
Particularly at the moment, I guess.
Yeah.
And,
sorry
China,
to remind you. Sorry.
Yeah. And China, as we've said, is kind of like this 5-year plan. If it gets in there, that's great, but we don't know. So CERN essentially gives the stability for the field. Yeah. And as part of that, like, I mean, as Patrick emphasized, like, a lot of the PhDs and whatnot, they are going into the rest of the community. And sometimes, like, as you said, derisively, it's viewed as like a workforce program. I don't think anybody views that the number of particle physicists has to stay stable or couldn't change by a lot. But one part I think that is important, that doesn't get emphasized so much, is we have certain technologies we're developing that really let us ask questions about the universe in ways nothing else can do. And if we don't have a direction such that these technologies continue to be developed, we could lose this part of expertise that we developed over the last century or so. So one thing that we're talking to experimentalists and theorists right now, accelerator physics is a very small field, and very few PhDs get trained in this. So if they don't have a direction that can bring PhDs into the pipeline and say, this is an exciting way to go, humanity could essentially go to a dark ages in terms of how we explore the shortest distances.
We're learning again how to land people on the moon, right? Because it was mothballed for however many decades.
So I think this is part of it. We're not saying like everybody needs jobs and we just give jobs to any particle physics. We're saying there is certain information humanity has accumulated, and we think this is valuable, and we need to sustain these directions of inquiry. It's not about day-to-day jobs. It's really about the science and the knowledge that we're developing in this field.
Very, 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 very well said. I also like that you've all flagged up my my next talk, which I'm sure I'll bug you about, which is pushing back on terrible arguments against particle colliders, but we'll talk about that another day. Patrick K., any closing remarks before we finish off on that question?
We need clarity. We need to unite, and but before that, we need to have a scientific discussions on the science we want to do and how to do best the science we want to do, and not the other way around, not based on projects
crowbar things
trying
into
to
the particular program.
exactly try to explain what fantastic science you could do with your favorite project. The logic should be the opposite, and I hope that the organizers of the strategy will lead the discussion in that direction. And if it works like that, then we will reach a conclusion.
Fantastic. I think that's a great place to leave it. Vava, I did what you asked as well, so that's a good place to finish. Thank you very much, all of you, for taking the time today. We've done a decent stint, and I really, really appreciate you taking the time. Some amazing points, and yeah, thank you very much for taking the time. I will make sure all of links to your work and your socials are down in the description, and hopefully when the next interesting thing comes up, we can get back together and discuss it again.
Sounds good.
Yeah.
Thank you very much.
Good.
Thank you.
Take care.
Thank you.
Bye now.
Hey, bye-bye.
Bye.
I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.